All right, let's go ahead and get started. Good afternoon, everyone. Welcome to the August meeting of the Science Engineering Council. Glad we could all get together. I'm sorry I can't be there in person, but we are here in a hybrid format every second Wednesday of every month. Most of you already know us pretty well, but for those who don't, feel free to join up, sign up, and join the SEC. We really appreciate that. That's kind of the lifeblood of the organization. And it's a little slow this time of year, people on vacations and such, but we're looking forward to today's conversation. And let's see, Cheryl, are there any new members to mention today? Or any other announcements? Okay, not at this time. Great. All right. Well, anybody else want to make any brief announcements before I hand it off to Yvonne? If not, I'll do that. Yvonne, if you could please take it away, and let's all talk about upcoming meetings and then get into today's discussion.
Great, thanks, Tim. Thanks, and hello to everyone. Today we are in the Community West Bank training room, so it's a different setup today. Joseph is switching cameras. That way a little bit. Where are you going to stand? Right there. Right there? Okay. So we're getting used to the new cameras and that sort of thing. But if people want to come to a future meeting, we've got more space and our speaker can stand next to the slides and the podium, that sort of thing. Our next meeting will be on September 11th, and we'll be sending out an email about the topic shortly. On October 9th, Dr. Alex Santoro, professor in UCSB's EEMB department, will be speaking on engineering biodegradable plastics for tomorrow's ocean. As always, feel free to contact me about particular topics or speakers you would like to suggest. And if you're interested in our past meetings, we have a YouTube channel with recorded meetings. Subtitles are available during today's talk if you enable captions in your Zoom window. And you can type questions into the Zoom chat during the talk or ask them after the talk. Today, we're pleased to have Dr. Susannah Scott speaking to us. She's a distinguished professor of chemical engineering and of chemistry and biochemistry at UCSB, where she holds the Duncan and Suzanne Malachamp Academic Initiative Chair in Sustainable Catalytic Processing. Her research interests include the design and disassembly of materials using renewable and recycled carbon. He's also an associate editor for ACS Catalyst. And a member of the board of reviewing editors for science. In 2014, she founded the Malachamp Academic Initiative in Sustainable Manufacturing and Product Design at UCSB, where she now leads an interdisciplinary program in research and education involving faculty from chemistry, chemical engineering, materials, environmental science, industrial ecology, technology management, political science, economics, and science communication. She received her PhD in inorganic chemistry from Iowa State University. Welcome, Dr. Scott. Thank you, Eva.
Oh, it's a pleasure to be here today, and thank you for turning out in August. It's steamy August, and especially for a chemistry talk. I guess they don't call you Science and Technology Council for nothing. I don't know if it's possible to make the screen larger again. Can we change the view? Awesome. Okay. So I hope this will be a discussion. Encourage you if I say something controversial and you want to challenge it, jump in. And if you're on Zoom and you want to put something in the chat, Yvonne will jump in on your behalf, or you can just interrupt me. But my goal today is to introduce a new way of thinking about plastics and a new way of thinking about carbon. Plastics are by far the largest group of stuff that we make out of carbon. There is nothing else that is on this scale apart from fuels, transportation fuels. And I think the world has a plan to deal with the carbon in transportation fuels. It does not yet have much of a plan to deal with the carbon in plastics. So this is, I think it's my contribution to trying to deal with this. I have spent a lot of my career making plastics. They are fascinating, beautiful materials. And now we have to unmake them, right? So every great technology eventually reveals that it has some challenges that have to be dealt with. All right, so as Yvonne said, I'm from UC Santa Barbara. I've been there for about 20 years now, working in both chemical engineering and chemistry and biochemistry on research involving chemical transformations of carbon. But I will start with something a little bit different. This is an old engraving of an English pirate, Henry Every. And in 1695, he attacked and captured probably the richest treasure ship that has ever been. This is the Mughal treasure ship, Ganji Sawai, and it was carrying at the time probably about 500,000 English pounds worth of treasure. Today, that would be in the $50 million kind of range. And he robbed the ship and he did other awful things. And he got away with it. Okay. So the law at the time governing piracy on seas had to do with what do you do when a crime is committed, an egregious, terrible crime is committed outside the jurisdiction of any nation. And the law that governs this is maritime law, and pirates are declared in maritime law hostis humani generis, which in Latin translates to the enemy of all mankind. Okay, so maritime law gives any nation the right to intercept and bring to justice any pirate who commits these crimes. Doesn't matter which nation the pirate belongs to or where the crime was committed. And this is all recounted in a beautiful book by Stephen Johnson, which he didn't give it a Latin title. He called it The Enemy of All Mankind, and I recommend it. Okay, so why am I starting with this? This year, 2024, it's entering later. We have World Earth Day. This was in April 22nd, and the theme of World Earth Day this year was planet versus plastics. So this is obviously an issue which has become very current. Lots of people worried about plastic pollution. And on the World Earth Day website is this statement: plastics are a danger to humanity and all living creatures, disrupting the delicate balance of life on Earth. And I mean, we've seen the photos, right? They often involve pollution in the oceans, parts of the world that we think of as international territory. They don't belong to anybody particular. They're not anybody's particular responsibility. But if they are truly a threat to all humanity, this is something on the scale of international maritime piracy. And it's a challenge to deal with. Okay, so that's the framing. Well, we go back to the beginning of plastics, and plastics were invented beginning of the 20th century or so by a chemist called Leo Baekeland. This is his reactor. He made the first plastics in this device, which he called the Bakelizer, which is now in the Smithsonian Museum in Washington, D.C. And the material that he made was a material called Bakelite. So Bakelite, I'll show you its chemical structure. If you familiar at looking at these things, you'll recognize that there are phenol molecules embedded in this structure, as well as formaldehyde molecules. So those are the components of it. You put them together inside the reactor, and they form this Bakelite material. I think it's really interesting, too, if you look at the symbol for Bakelite. This is an old advertisement that I pulled off the internet. You see the infinity symbol here? It didn't initially symbolize infinite lifetimes, which is what we reproach plastics for today. It symbolized an infinite number of uses. Okay, so people were thinking this is going to be an incredibly versatile material. And places where you may have encountered Bakelite, okay, when I give this to my students, they go, we don't recognize those things, but but I do. Okay, so do I. Yeah. So Bakelite is the plastic that old telephones used to be made from, the plastic that radios used to be made from, some jewelry. And for me personally, okay, my if you were in a school band before you decided whether or not to buy a very expensive wooden instrument, you would buy one that was made of bakelite. Okay, that's the material. Okay, and ironically, this material, which we would all call colloquially plastic, is not actually a plastic. It's a material called a thermoset, which is different from a material that we would call a thermoplastic. But today, everybody puts them in the same category, and I'll explain the difference. All right. So at the time that bakelite was invented and other polymers started to become available, these were lauded as having huge potential environmental benefits, as well as commercial benefits. One of the reasons is that it sort of coincided with a big expansion in the production of oil, crude oil, and oil was displacing natural products at the time. Okay, so it's ironic that, you know, over 100 years later, we're now saying we ought to be using natural products instead of synthetic products. But at the time, think about the natural products that were being used. People were lighting their homes in the evening with whale oil, okay, and killing whales to get it. So having something that didn't require killing whales was considered a really good thing. In the case of the plastics, to make that more specific, things like combs or billiard balls, and actually there are many examples of these are just two that you will recognize, were also made from natural materials, and you killed animals to get these natural materials. And so the idea that you could replace a tortoiseshell comb with a bakelite comb, which resembled it and cost a tiny fraction and did not involve killing a turtle, was considered a good thing. The elephant tusk billiard balls were replaced initially by celluloid billiard balls. Celluloid is nitrocellulose. If you're a chemist, and I can see Mary thinking this, these billiard balls strike each other, smack, and nitrocelluloid is explosive. You can imagine this is not the best choice of a polymer to make these things out of. And so now they're made from phenolics. So they're synthetic materials replacing natural materials. And for a big part of their history, this was considered a really, really good thing. Okay, so this entered the world of consumer goods as well. Artists love this stuff. These materials are truly thermoplastics. And a thermoplastic is a material that when you heat it, it melts. And you can shape it in a mold into whatever form you like. Okay, so the bakelite material that I showed you is a thermoset. When you heat it, it becomes rigid and you can't change its shape after that. But the thermoplastics were really the ones that took off, and people love to make stuff out of them. So these pieces of furniture today are actually in museums. They are incredibly expensive, and I think artists love making them. The last example, these monoblock chairs, are incredibly cheap. You can go to a hardware store and buy these for a couple of bucks, okay? Which is why they have spread through the entire world. They are everywhere in the richest and the poorest countries. And, you know, this has transformed the way we live. Plastic has transformed the way everybody lives. Partly because these materials are so versatile and so inexpensive. All right. Obviously, entering popular culture, and many of us have seen this movie. They have actually, you know, plastic. You can talk about paying with plastic, or at least we used to before people started paying with their phones. So this is on the way out now. But the number of these plastic cards is just enormous, and I'm not even including here the cards that are used to get into hotel rooms, right? There's even plastic money now, and actually I brought some, because it was in Canada a few months ago. And I don't know if anybody's seen this stuff, but it's actually pretty cool. So if you want to take a look at it, you can pass it around. This is a Canadian money, which is made from polypropylene. And it is very, very hard to counterfeit. We all know that American money are extremely taxing. It's actually quite easy to counterfeit. And it wears out. And this plastic is considered indestructible. Of course, if you heard what I just said about plastics melting, you'll want to make sure that you don't get get too close to a flame because you can burn that pretty quickly or melt it. But anyway, this is, plastic has become or became over the course of the 20th century, really. Okay, so we have this sort of over the course of a century, but really it is the second half of the 20th century, a huge expansion in the production of plastic, a compound annual growth rate of 8.5%. And if you would compare this to some other construction materials over a standard period of time, you see that plastic growth has actually gone much further than other construction materials like steel and aluminum. So, this about a 40-year period between 1980 and 2017, the production of steel tripled, the production of aluminum quadrupled, plastic a factor of 6 nearly. And it shows no sign of slowing down, okay? So the amount of plastic that we make depends on uses that we find for it. It also depends on the fact that parts of the world which are becoming richer and are wanting more consumer goods are now using more and more plastic. And I don't think we could say that those countries becoming richer and their standard of living rising is a bad thing, right? We want them to have the same standard of living we have, and that means that the consumption of all of these things. Okay, so this is a breakdown of where plastic is used. We keep finding new uses for it, but it's notable that about 40% of all plastic that we make is used in packaging. And that is inherently a short-term use. Okay, the packaging may sit on the shelf or in the Amazon warehouse for weeks or months, but it arrives on your doorstep, you open it, you throw out the plastic. Okay? So lots of short-term uses. Other uses for plastic are getting shorter. And the reason is that these devices, electronic devices, things associated with other activities, we're getting richer, the products are getting cheaper, we throw them out, we buy new ones more often. And so there's just a huge amount of this material that's being generated. And the consequences are that in some places of the world, the beaches look nothing like the beaches in Santa Barbara. Okay, this is a beach in Mumbai, India, and most of the waste on this beach is plastic. This is a tragedy. And it's not just the beaches, obviously, it washes up there from the oceans. I wrote a paper with a colleague and some students about 4 years ago now, where we looked at the degradation rates of these plastics in the environment. We didn't do any research for this paper, we just surveyed what's in the literature and looked at these degradation rates. And you can see them surveyed here for different types of plastic. These are the recycling symbols that you see on the bottom of your plastic. So different kinds of plastic with different symbols. But all of them have extremely slow degradation rates, including number 7, which is the biodegradable ones. Okay, so biodegradable plastic, polylactic acid being the main one, is actually not very biodegradable under real environmental conditions, right? You have to industrially compost it to get it to degrade quickly. So this paper, which was just a quick literature survey, and there wasn't much to survey because there's not much information out there on this, quickly became my most highly cited paper by a mile. Okay, it was amazing. I keep looking at this. I pulled these statistics off the web last night, and when I first saw this, I had to look up what is an altmetric score. So article views is kind of obvious, but altmetric is the number of times you've been tweeted or posted on Facebook or mentioned in the popular press or something like that. So this was an idea that caught a lot of people's attention. How do we know how long those plastics are going to be there? People are making estimates, and you've probably seen these in newspapers. The plastic bags live for 100 years, the bottles live for 500 years. Well, they haven't been around for 100 years or 500 years. The materials have not existed that long. So how do we know? How do we know? And basically what we're doing is extrapolating. And it's a very long and very uncertain extrapolation. So, that was part of what this was about. But what we figured is that if you took these degradation rates, if you just took an average, you see the error bars are enormous because we don't really know. But if you just took an average and you made some predictions about how long a piece of plastic would sit on a beach, you'd come up with a wide range of estimates, okay? So we did the little back of the envelope calculation for a 5.5 gram piece of polyethylene. If it's a film, so film is very thin with a very high surface area, it would degrade if it degraded at this average degradation rate in a couple of years. Okay, would not be there anymore. But if it's a bead, the bead is what the industry actually manufactures plastic as, and then you melt them and mold them into other things, right? If you had a bead, it could easily live for a millennium or more, okay, because it has a much smaller surface area. So what is the right answer to how long is that plastic going to be there? I don't know, right? That's a really big range, but it's concerning, right? It's truly, this is concerning. All right. So I want to talk about what's the real problem. And I'm sure that you have heard not just about the fact that there's plastic trash on beaches around the world and it's, being ingested by marine organisms. We think of those as macroplastics, big pieces, right? But people are now detecting in all kinds of places, in the water particularly, microplastics, tiny pieces that we didn't think to look for before because you can't see them with the naked eye. But when you drink from a bottle, a plastic bottle of the water in it, you are ingesting microplastic. You are, okay? So the question is that a concern? Okay, it's certainly a scientific question which merits serious investigation, and those investigations are ongoing. But people want to know now, is it a concern? Right? How worried should I be? All right, so a bit of a cautionary story, right? There was a study that was published just 3 years ago, which has been cited 417 times in the scientific journals, as well as a lot of times in the popular press as well, saying that the amount of plastic in our drinking water is such that every week we ingest about 5 grams as microplastics. And 5 grams is about the mass of a credit card. So the World Wildlife Foundation, which funded the study, came up with this ad, which you can still see on the net today. It's even been in news articles in the last couple of months. I checked, saying that every week you eat about a credit card's worth of microplastics. I mean, that's scary, right? That's a lot. And you think of that over the course of your lifetime, how much plastic have you ingested and what does it do? What does it do to you? Well, the thing is, this is wrong. Okay, it's egregiously wrong. And there's a calculation error in this paper. The paper has not been retracted, by the way. And the error is being pointed out not by the chemical industry or the plastic manufacturers, but by life cycle people working in this field, saying that the calculation is wrong. And the actual mass is about 1 million times smaller than what's in that paper. And so it would take you 23,000 years to eat a credit card worth of microplastics. The amounts are far, far smaller than people are. But the fact that you can correct an error in the scientific literature doesn't mean that it's corrected in the public perception. Not for a long time. Okay, so these are tiny amounts of things, and this certainly is scientific investigation. The answers are not clear yet. The fact that we can detect things doesn't mean that we can detect the outcomes yet or predict them. Yeah.
So on the other hand, though, the amount of microplastics that we're getting exposed to is going up exponentially as well, right? Because you have all that crap that's already out there that's degrading and hitting the food chain. So a year from now, we're going to be eating a lot more microplastics than we were last year, et cetera, I assume. There was a question that popped up from Kathy King that I saw. And this kind of gets to the same question, which is, if you take a plastic bag and it degrades, you get microplastics, which is just a smaller set of molecules clumped together. When you talked about your degradation curves, was that where you actually break the final molecule is broken apart from its plastic molecular structure and it's becomes some other components of those atoms? Or does it just keep getting smaller and smaller and you're just dealing with smaller bits of microplastic?
Well, I think there's about 3 questions there. So let me say first that I don't know if the amount of microplastics that we're being exposed to is growing exponentially, right? The fact that we've only been detecting them for the last couple of years means that we don't actually have a time frame that would allow us to show that in the data yet. Okay, it's true that there's more plastic going into the environment. I would say that one possibility is that when you get to the micro or nanoplastic size, you really have a pretty high surface to volume ratio, and you are getting to you're getting closer to the point where these molecules, they're still large, but they are small enough to be biodegradable. Okay, so it is the very, very large ones that take a long time to break down. When they become very small, we think they break down much sooner. Okay.
But biodegradable is the definition of that, meaning that it's going to break down into its component atoms, or is it just again just a smaller piece of the plastic?
I think it depends how it breaks down. So if something is broken down by a microorganism, the fungi in the soil or something like that, they can mineralize it. They can turn it into CO2 and water. But the chemical processes that break these things down tend to break the chain somewhere and create two smaller fragments. And then those chains break again and create smaller fragments. So there's a variety, there's a lot of mechanisms, and it's actually very specific to what the structure of the plastic is. Plastics have a lot of different structures because there's a lot of different kinds of materials.
That would be interesting stat to know, because I've never seen that. I've never seen anywhere anybody define biodegradable. Does it get to its mineral components, or does it get to just a smaller piece of plastic?
So it's an extremely important point, because some of those molecules, the components, are pretty hard to degrade, and they are not necessarily benign either, right? So the idea that we can throw our biodegradable plastics in the ocean and have the ocean just break them down really worries me, because we are generating molecules in the ocean then that things that live in the ocean are going to be ingesting, right?
That was my first point.
Yes.
Well, you don't have to eat a whole credit card to be a problem. Those tiny microparticles cause problems in, hearts or livers or kidneys, or a lot of operation.
You're right.
That's really the problem, isn't it? I mean, a small amount of very small things can cause a very big problem in certain organs.
You're exactly right. So that's why it's really important to investigate that. And I would say the first phase of discovering this problem is just identification. People are measuring stuff that they could never measure before. Okay, so that's good. Now we know it's there. The next phase is figuring out what's it doing. And I think there is actually very little hard scientific evidence so far. So if you look at these papers, look at these newspaper articles and the ads on the web that are saying this is terrible, you're all going to die. It's based on the fact that the particles are there. It's not based on any studies of what the particles actually do yet. And those studies are so we should be looking for what comes of this for sure. Okay, my personal feeling is that these things cannot be acutely toxic. If they were acutely toxic, we would have all been suffering from this a long time ago, and we clearly haven't, right? But the longer term effects, the effects over a lifetime of that cumulative exposure could be significant. And there's not a good way to know that without doing long time scale experiments, right? And that's, so obviously it's going to take a while before we know for sure. I think, was there a question online? Or did we catch it?
You got it.
Yeah, same question. Yeah.
Okay. All right. So if you're worried about microplastics in the oceans, the first thing to ask is, where do they come from? Right? Are they coming from my bottle of water or someplace else? Because we want to target our efforts correctly in terms of where do we try to prevent them from being generated. So 3 big sources of microplastics in the oceans. The first is synthetic textiles. Okay, so we make a lot of clothing from polyesters, polyamides. Those materials, when you wash them, generate microplastics. That wastewater from your washing machine goes to the city treatment plant, and then eventually makes its way to the ocean. So that's about a third. Okay, it's from your washing machine. You can imagine if you want to make a difference, you should target that. You should put filters in the washing machine. You should make your clothes out of plastic fibers that shed much less. There are strategies you can imagine, right? So textiles is one big part of this. things actually that people do not really think of as being plastic, right? Are we all wearing plastic today? I guarantee that we are somewhere, okay? But we don't think about that, right? We think about other kinds of things. Another big source is car tires, okay? So the whole point of a car tire is that it abrades, right? That's how it smooths your ride. That's how you brake, et cetera, et cetera. We don't have a good replacement material for car tires. And so car tires are a big source of these microplastics as well. And hard to think about how we could mitigate that. In fact, electric vehicles with their big batteries tend to be quite heavy. And so their tires wear out sooner. So they're contributing more microplastics to the environment than conventional cars. That's a question. Somebody with the right question will think of a clever answer to that question. But if you're not asking the right question, obviously you're not going to get there. City dust. I was just thinking about the new striping on Hollister. Okay, those stripes contain plastic, and we drive on them, and that stuff generates a lot of dust. You know, eventually they wear off, right? Where do you think they wear off to? They create little particles that abrade, and that stuff is plastic. So there's.
Hi, you have reached the office cell phone of Dr. Ayana Tripathi. Please leave me a message and I will get back to you as soon.
So there's lots of sources of microplastics. What you don't hear about in terms of the production of microplastics are these kinds of things. Okay, and you know, is this a significant source or not? These are macroplastics, macro pieces of pollution. The micro pieces probably have other more significant origins. Okay. So you do hear about people saying, you know, we should stop using plastics. We've got to stop. And the challenge there is that plastics have become so embedded in our lifestyles that it's really not a question anymore of plastic grocery bags, right? Our entire food distribution system, along with food safety and food preservation, is really, really highly dependent on the use of plastics. And you might be thinking, surely there are other materials. We'll get to that in a second. But I want to also say that our hospitals and our healthcare systems depend very, very much on what is necessarily single-use disposable plastics. In fact, hospitals were much less safe places before these materials existed because materials would be reused and the chances of contamination were much higher. So as we talk about changing our relationship to plastic, we have to proceed with caution and make sure that we don't interrupt some of these very, very important uses. Okay, but people say, yes, but plastics are just, you know, awful for the climate because we make them from fossil fuels and they have so much carbon embedded in them, and then we throw them away, and that carbon ends up in the atmosphere eventually. As we make more plastics, there's going to be more of those greenhouse gas emissions. That's all true. Okay. The question is, right now, the one that I'm thinking about the most is how do we change this for the better, right? So when you're thinking about a life cycle, you can't just think about removing something from our ecosystem. You have to think about what replaces it. And so it's a comparison. You have to think about the comparison. And some of these ads don't actually talk about the comparisons. So I did one from, actually, this was a talk I gave a month ago, but I did one for myself. Okay. Think about your 4 kilogram or 1 gallon milk jug. Okay. This is made of high density polyethylene. And it's pretty amazing material because this gallon plastic jug, if you were to replace it, say with glass, you could, right? We used to get milk. Some people used to get milk delivered in plastic in glass bottles, and glass 1 pint bottles. And if you take 8 pint size glass bottles, you could also transport 4 kilograms of milk. So the analysis, though, says that the amount of polyethylene that holds a gallon of milk is 2 milligrams. That 2 milligrams is what the bottle weighs. And you know, the amount of carbon dioxide that is emitted in the production of that plastic is very small. If you look at the glass, the mass of those 8 1-pint bottles, it's half the mass of the milk. Okay, so you can quibble with my numbers and they would shift a little bit, but the fact is that the amount of glass is hugely more than the amount of plastic to do the same job. And the amount of CO2 emissions in creating that glass is orders of magnitude higher as well. So if you said, let's all mandate that everybody sell and buy milk in glass bottles instead of plastic bottles, because we wouldn't have microplastics then, we would have impacted the atmosphere in a different way. Okay, and so there are trade-offs here that we have to confront as well. All right, so I came across this ad. Actually, you start clicking on these things, they'll send you all kind, right? This is a marketing for trash bags that are being marketed as not plastic. They are not plastic, okay? And I'm looking at this ad thinking, that looks like plastic, right? If it's not plastic, what is it? Okay, so the marketing on their website says it is made from plants, not plastic. Okay, all right, that's a bit of a mystery because plastics can be made from plants. And if you could dig a little bit deeper and say, what kind of materials are you making from these plants? They're making plastics, okay? They're making polylactic acid. That's the one I told you, it's marketed as biodegradable. It's not unless you put it in an industrial composter at an elevated temperature. And this polybutylene adipate terephthalate. So yeah, it's hard to come up with replacements for plastic that are as lightweight, as energy efficient. And as we're trying to make this transition, trying to think of good alternatives, we need to not get stuck in the marketing track. We want to stay in the science arena. Okay, so people do this, life cycle people do this. They compare life cycle for bio-derived plastics with oil-derived plastics, okay? So the bio-derived plastics are the ones in red here. So PLA, that's polylactic acid. That's the one I just showed you that those plastic bags were made from. Okay. The ones in black are the oil-derived plastics. So here's polypropylene, polyethylene, polyvinyl chloride, those kinds of things. Okay. So looking at these in terms of their life cycle environmental impacts, as well as their sort of greenness, whether they come from biosources or not. The place in this diagram where you want to be is up in this top right-hand corner. That's the best, okay? And what you see is that all of the so-called biodegradable plastics, the ones that come from plants, score very high on these green chemistry principles, but they have higher life cycle impacts than the fossil fuel ones, okay? So the analysis here is that these plastics, polypropylene and polyethylene, use less energy and have lower environmental impacts than biopolymers in every LCA category that this study examined, okay? And these are not people working for the chemical industry. These are LCA people who ask these questions. So the answer is that at the moment, it's actually difficult to think about just replace one material with another material. We would be replacing one set of problems with another set of problems, and eventually we would figure that out and say, oops, we should have thought about this a little bit more. Okay, so it's clear to me that the issue here is a waste management challenge, and we have to get a lot better at waste management because we don't want these things getting into our food, getting into the ocean. And so today, what we have in plastic manufacturing is this big, largely linear life cycle, okay? So it doesn't matter whether you start with fossil-based plastics or bio-based plastics. Bio-based right now is a tiny, tiny stream compared to fossil-based, right? You make the primary plastics, you make stuff out of those plastics, then you throw it away. And here's what happens to it when you throw it away. There is a tiny, tiny recycling loop. Okay, most of it does not go through this recycling loop. Most of it is either incinerated or landfill. Which one depends on where you live in the world. Okay, Japan incinerates most of its plastic waste because they don't have space for landfills. The US has lots of space, we landfill most things, okay? That's, but 3/4 of this plastic ends up there. 20% of it leaks. And by leaks, I mean, it doesn't actually get to the landfill or the incinerator, and it doesn't go into the recycling stream. It ends up in the environment. And that's a tragedy. That's the part that we have to fix, right? It's unacceptable. So, my colleague, Roland Geyer, who is in the Bren School at UC Santa Barbara, wrote a very influential paper in 2017 talking about how much plastic we have made, how much more we are going to make. And because it's an exponential growth curve, it's, you know, pretty clear that in the next 20 years, we're going to make as much plastic as the world has ever made, right? And you can extrapolate on from there. And most of this still exists, okay? Not much of it has been incinerated. Most of it still exists, and it's sitting in our landfills or it's in the environment somewhere. So, as I said, worldwide, very little plastic gets recycled, less than 10%. The US does particularly badly on this score, right? Because we don't recycle much. And here's a very interesting sort of prediction that came from the Ellen MacArthur Foundation, calculating how much plastic is going to be in the ocean relative to the mass of fish. Okay, so today there is more fish in the ocean than plastic, but if we keep doing what we're doing, then by 2050, there will be more plastic by weight in the ocean than fish. Oh, we cannot allow this to happen. We just cannot.
If there are any fish alive.
If there are any fish left, yes. If the fish population declines and all the plastic, yes, I didn't look into the assumptions that they use in generating the statistic, but it is frightening, right? So it is clear that we have to do something about this. Okay, so recycling. Let's talk about recycling. This is a scary quote from a book on recycling. People for a long time have believed in recycling. They are starting not to believe in it so much anymore. Okay, but I mean, for a long time, people did believe and did try to recycle. So what happens when you put plastic in the recycling bin? It's supposed to get recycled, right? But it actually didn't. It didn't get recycled. And the reason is that until quite recently, much of our plastic waste was not recycled here. It was shipped overseas, where we hope that they recycled it, but we don't actually know what they did with it, okay? And most of it went to China, frankly, okay? So this is not just true of the US, this is true of everywhere in the world, sent their plastic waste to China. And when I saw this picture, I was a little bit baffled because honestly, plastic waste is trash. It has no value. How are we paying to ship it halfway around the world? How does that work, right? Like, who pays to send it to China? And why does China want it? Well, they don't want it anymore because they've stopped importing our plastic waste. But it was actually somebody from Dow Chemical who explained this to me. We buy an enormous amount of stuff from China, right? These container ships arrive at the port of Los Angeles every day and offload all their stuff. And you know what? Then they're going back to China to pick up more stuff and they're going empty. So the plastic trash hitches a ride. It goes back there. And I don't know, I think the Chinese used to pick out some things that were valuable in it. The rest, I don't know what happened to it, but this what happened, right? We were sending all this stuff for free to China. And in 2016, China said, we don't want your trash anymore. And what this did was force us to reckon with the lack of a local recycling or a domestic recycling capability. We never built it, okay? And so there is nothing now that we can do with our trash until we figure out how to recycle. Okay, so everybody thinks they're recycling. They're not actually recycling, but you've probably seen these symbols on plastic pieces and you think because there's a recycling symbol, it can be recycled. That's actually not true. There's only 3 of these symbols that actually indicate that your plastic is in any way recyclable. The others are just effectively not recycled at all. And these 3 are basically PET, which is the plastic that the bottles are made from, polyethylene, which is the milk jugs, okay, and some polypropylene. Okay, those three plastics, there is some way to recycle them. The others, not so much. Okay, so let's talk about how you recycle them. These are just random pictures. I pulled these from the internet to show the kinds of things which are in that category 2, polyethylene. Okay, so grocery bags for sure. Okay, but also cable insulation, medical equipment, water pipes, bulletproof vests. So let's say that you have a big container full of all these different kinds of polypropylene and you melt it, polyethylene, you melt it, and you say, who wants to buy my stuff? It's gunk, right? Nobody wants that stuff. None of that mixture does not have the properties of the original, of any of these original materials. Okay. And that is a problem with plastic recycling. It is fundamentally, you're taking materials which were highly engineered for a specific purpose, mixing them together to make a material which has no properties that anybody wants, and then wondering why we don't have a recycling industry for this. Okay, this is a very challenging problem. This is what we call mechanical recycling, right? All we're going to do is melt the stuff and let it resolidify and try and find a use for it. And there are a few uses, okay? We can make plastic lumber, we can make playground equipment, we can make benches. These are low-grade uses, right? So that is mechanical recycling, and its versatility is limited. Okay, so what are other options? These are the things that, this is how we make things out of plastic. And of course, we can landfill. That's the linear life cycle. We can burn our plastic and we get some of the energy back out again. Okay, get through all of these. We can pyrolyze the plastic, right? So you can heat it at high temperatures in the absence of air, and you turn it into a fuel. So you could fuel cars with it. That generates energy, but it also generates CO2. And we've been thinking too about this intermediate cycle. So this is different from directly reusing. As I said, there's limited applications for that. It's different from pyrolysis, where you're just trying to make something you can burn. We're actually trying to make something which is useful, which can be remanufactured. And that's called, I mean, until recently it was called feedstock recovery. So we want to depolymerize the plastic, get the molecular building blocks back, and then we can repolymerize it and make whatever kind of plastic with whatever properties the customer wants, right? If we could enhance that cycle, which is kind of circular, right? Monomer to polymer, back to monomer, back to polymer. If we could make that work, you would give the waste plastic a value. And if you give it a waste plastic of value, then people don't throw it away. Okay, right now it has very little value. Okay, so we need to recycle smart. Yes.
Does the burning take it down into its mineral components?
Well, hopefully, right? But you know, municipal incinerators have to have very carefully controlled conditions to make sure that they're not emitting other things which are toxic. So if you get it all the way to CO2 and water, you're good. But you have to spend a lot of effort to get there.
And then what about the pyrolysis? Does that get it down to its, I don't know what naphtha.
Naphtha is a fuel. Okay, so you can think of that like gasoline in your car. Okay, so you can turn plastic into gasoline if you want.
Because you can use pyrolysis in lieu of burning and get it down to the same components, I think. You just never.
Well, but the goal is to burn the naphtha eventually anyway, right? So it's just whether you burn it directly or you turn it into a liquid fuel that you're going to burn. So both of those are possible. All right. So if we're going to tackle this problem, again, I'm going to ask, what's the right problem to tackle, right? And so people will be devising all kinds of clever ways to recycle things which make such a small contribution to the waste problem that I would say, okay, that may be good, but we still have this big problem to solve, right? So if we look at all the plastic production, 3/4 of it are these 4 plastics. These are what we call the polyolefins. And these are the ones that are creating most of the trash. So in my view, these are the ones that we have to figure out how to replace or recycled. Okay, and this is where my work comes in. This is what I work. So the world makes about 200 million metric tons of these polyolefins every year. And in terms of their chemical structure, they are almost identical to crude oil, from which they are largely made. Okay, what that means is that their energy content and the chemistry required to transform them is the same chemistry that we use for transforming crude. Okay, if you start looking at other sources of carbon, like biomass or CO2 from the atmosphere, their energy contents are so different that you have to put in huge amounts of energy to make polymers out of them, to make new polymers out of them. And that has serious implications for greenhouse gas emissions. So the opportunity here to make new things out of these waste polyolefins is a climate-based opportunity as well as a chemistry-based opportunity. All right, so going to thermodynamics. Maybe you haven't seen this since you took chemistry in college, but it's important, right, to think about this. Okay, so let's say that I want to make polypropylene. It's a very common large volume polymer. I want to make polypropylene, and the raw material is propane. Okay, so to make polypropylene, I can't polymerize propane directly. I have to turn the propane into propylene, and that is a huge uphill in energy kind of transformation. So I put an enormous amount of energy into the propane. I can turn it into propylene. The propylene is called the monomer. That's the building block of the polymer. Then I take the propylene and I polymerize it, and that is a hugely downhill in energy process. So I get the energy back again. All right. So if I want to turn this process backwards, if I want to run backwards and do chemical recycling, the worst thing I could do is take my polypropylene and try to make propylene out of it, right? I have to put a huge amount of energy back in so that I can polymerize it again. Okay, so that energy very efficient. And that's why we don't do that. Okay, so this is the life cycle of polypropylene. We make it from propylene, and then we throw it away. And the reason is that the energy required to the energy released when you polymerize these propylene C3H8 monomers to polypropylene, that's a price, and you got to pay that price again when you make the propylene again. Okay, so anytime you have to put all that energy back in, that's greenhouse gas emissions. All right, so what we did was come up with a way to get around the thermodynamics, and it involves not one step, but two steps. Okay, so here's the idea. This is a polymer. This is actually a polyethylene polymer. Okay, and you can see, so every line here represents a bond between two carbon atoms. And when there are two lines, it's a double bond between two carbon atoms. So I can do a reaction, which is called olefin metathesis. And this reaction is done with a small molecule, ethylene. These two double bonds exchange ends. And when I do this reaction, which I call ethenolysis, I'm cutting the chain with ethylene. I'm cleaving that double bond right there. Okay, so a long chain becomes two small pieces or two shorter pieces. Both of those pieces have a double bond now on the ends. And in order to do this again, I have to move that double bond into the middle of the chain, and then I can cut those pieces again. And so repeat these two steps again and again and again. The final product that you eventually get out of this is propylene, that monomer for making polypropylene. And the enthalpy cost, this is a small number. This is near zero, and it's actually a bit negative, which means this is a favorable process. If I have a good process, I can do this at room temperature. Okay. You can rarely do these things at room temperature. You just have to push them a little bit and have the right kind of catalyst, but this is not a hugely energy intensive process. Okay. And it's selective. It'll give me one product, propylene, which is then great. I can use that to make polypropylene. Okay, so that's the idea. Does it work? Well, we recently showed that it does work. These are reactor data. The reactor contains polyethylene and ethylene and a catalyst. And you can see here the formation over time, over several hours, of propylene. And the selectivity to propylene, that's the green line, is 95%. Okay, so we can depolymerize polyethylene into propylene. This reaction was done at 100 degrees Celsius So this is not pyrolysis conditions. These are considered fairly mild conditions. And we're actually taking polyethylene with propylene. Okay, so at the moment, this is just a clever chemistry demonstration. Could this actually be commercialized? Yeah, I don't know. So what are some of the other things that you could make from waste plastics? Obviously, every plastic will have its own target. So I'll talk mostly about polyethylene, but there's lots of things that you could make from a plastic like polyethylene, right? So this is the original structure of polyethylene. This is a sort of rough energy diagram. There are things that you can make which are thermodynamically uphill. You have to put energy in, no getting around that. Thermodynamics is a law. And there are things which are downhill, right? And you don't have to put any energy in, that just happens. And you usually have to add something to get these downhill reactions to work. So I'll mention a couple of these very briefly. This is a small molecule, not a polymer molecule, but the carbon-carbon bonds here are all single bonds. This is an alkane. It's a saturated hydrocarbon molecule, okay? If you want to make this, you can. All you have to do is take the polyethylene with an appropriate catalyst and hydrogen. Hydrogen now cuts the carbon-carbon bonds, caps the ends with hydrogen, and you get small molecules out of this. So we know how to do this now. Here's another example. This is going uphill this time to make these aromatic molecules. So the rings, what are these used for? I'll get to that in a second, but basically our reactor, we put the waste plastic into the reactor with a catalyst. We heat it up so the polymer melts and starts to interact with the catalyst. What comes out of the reactor are these two kinds of molecules. The top one is a long hydrocarbon chain. Okay, these are the lubricant style molecules. So they have a market. The bottom one is interesting because if you sulfonate that, you make an anionic surfactant, a detergent. Okay, so this is an alternative way of making detergents from waste plastics. And we do it in a very simple way, just put everything in the reactor, turn it on, and this is what comes out of it. Okay, we can tune the chemistry, and this is what my group gets really excited about doing, is that we can look at the effect of the hydrogen pressure in the reactor in terms of what comes out. This is the yield of aromatics, which decreases as you increase the amount of hydrogen. But interestingly, there is, there we go, a nice, in terms of the rate, this is the turnover frequency. The rate is a maximum at some low pressure of hydrogen because the hydrogen is cutting the long chains into smaller chains, and then the catalyst is causing them to aromatize, okay? So we have the conditions now to do this reaction very efficiently. And the interesting thing about this is that if you look at the conventional process for making these molecules, it's very involved, okay? So this is what we call a linear alkylbenzene or a lab. It's made by dehydrogenating an alkane or oligomerizing ethylene and then alkylating a benzene molecule. So anyway, multiple chemical steps. It's a dirty, dirty process. And I've just told you that I can take in one step waste plastic and make the same molecules. Okay. And the reason this is important is that if you're going to propose a new process, it has to compete with the existing process. The existing process, if it's really cheap and easy, is going to be hard to displace. So if you have a preferred feedstock for this process, because it makes it cheaper and easier, you don't have to pass laws to make this happen. You don't have to tell people they have to pay more for their detergent. It just works. It just works. And so we're talking about this. Procter & Gamble saw this. They got excited. They said, you know what? We could have shampoo where the bottle is made from recycled plastic and the shampoo in the bottle is made from recycled plastic. Our whole product would be, people would, I don't know. Maybe they could. We'll see. Okay. So the idea, I'm going to wrap up quickly here. The idea is that there's a whole bunch of things that you could make from waste plastic. You have to do the life cycle assessment, make sure that it makes sense to make these things from recycled plastic, but you could. And again, people are just, developing these ideas now and thinking about whether we can use this source of carbon, this energy-rich plastic carbon, as a way to make all the things that people want and need. So if we look at this sort of circular carbon idea, where we don't just refine the carbon and then throw it out once we use it. We want to recapture it. We want to make new things out of it. Manufacturing in the US, parts of it is very energy intensive. The chemical industry is the most energy intensive part of US manufacturing. Some of that energy goes into the feedstock, the carbon that we use to make stuff, and other parts of it goes into the energy to transform that carbon. We can decarbonize the energy part because we can electrify stuff. Okay, it's not easy, but we can. You can't just replace the carbon in the products. So that part is where we need to recycle the carbon. And the future is, I think, not solely mechanical recycling. That has a place, but it's a limited place, as I said. But that what we need to learn how to do is to take these big molecules apart and put them back together again. And if we can do that, we can truly recycle the carbon. What that allows us to do is think about the inputs being things like biomass. And I told you how energy intensive that is. We want to do that because we want to use renewable carbon, but we want to use it once every 10 times we use that carbon. Okay, not every single time we use that carbon. So that's how you pay that energy cost. You pay it down by making multiple uses of that carbon. And of course, you never recover 100% of the waste. Some of it is always lost. And so you have leakage of carbon out of the system as well. So the inputs and the outputs have to match, obviously, but a lot more recycling. All right, so I'll end with saying that maybe one day, instead of shipping all of our plastic waste to some developing country that is going to pick it through and try and find something of value, and we're not going to have to think about it, maybe if we see this as an opportunity and we have the capacity to use it, we will see people sending their plastic waste to us, right? Because it has value and because we can make important stuff out of it. And I used to call this the two birds with one stone. That sounds cruel. So I like the Indian way of talking about this. This is two mangoes with one stone. We get to keep using these wonderful materials in places where we really don't have suitable alternatives. We get to keep them out of the environment at the same time, and we get to minimize the greenhouse gas footprints. So that's all I have, and thank you very much for listening. I'd be glad to continue the discussion after this.
Thank you very much. We have a couple of questions from Kathy in the chat. Kathy,
Okay.
if you want to unmute, go ahead and ask things.
Sure. Thank you so much for this really amazing presentation. When you talked about the glass and the amount of energy it takes to make the glass, does that take into account that when it's reused, it's going to pay back that and ultimately have a negative impact versus the plastic jug that can't be reused?
Yeah, so that's a good question. I mean, glass is easy to sterilize, right? And that is super important for food uses and for medical uses. You have to be able to sterilize things. So the thing, though, is that you have to recover the glass. So people have to send it back, and you have to transport it. That's transporting glass is heavy, so you have to transport it to some facility where this is going to happen. Then you have to wash it, and then you have to sterilize it. And so by the time you take all of those things into account, it's actually not as energy efficient as thinking, well, glass can be infinitely reused. So I didn't take that into account in my calculations, but there is a recent paper, and if you're interested, I can give you a reference that did the full life cycle analysis on glass. And glass is the worst packaging material in terms of its greenhouse gas footprint. So they ranked other materials, and I don't think plastic comes out on top. I think cardboard does, but of course you can't package everything in cardboard. Some things are not suitable for that. So we need to do more of this, but I'm predicting that the public is not going to be particularly paying attention. Just think about the life cycle assessment of paper bags versus plastic bags and how that went. People basically ignored that life cycle assessment as well.
Right. Thank you. I mean, I guess I have another question if nobody else does. I don't want to monopolize. But when you talk about the different types of recycling, the chemical processes, does that also take into account the amount of energy that it takes to make the plastic in the first place? And do you know how much of that is being recovered in those processes? Because I've seen that, and maybe this is also debunked somewhere, but that 8% of global fossil fuels are used in plastic currently.
So the 8% number doesn't surprise me. Making plastics consumes about 3 or 4% of the world's energy. Plus you have the embedded energy in the plastic itself, which is about the same amount again. So 8% would make kind of sense on that. In terms of the different recycling options, the best one in terms of energy use by far is mechanical recycling, right? If all you have to do is wash something, melt it down, and make a new product out of it, that's the lowest energy footprint. The problem, as I said, is that that doesn't give you all the variety of materials that we need. It gives you a very, very small number of materials that tend not to be high value materials. So it's hard there even to pay for that kind of recycling. The incineration gets you back about a third of the energy invested in making the plastic in the first place. Okay, so that's not nothing, but I would say if you can do better than that, you would want to, because you just throw away 2/3 of the energy. Pyrolysis, again, I don't think you get back anywhere near the amount of energy that you invested in making the plastics. So mechanical is best when you can do it, but it's not often that it works really well. And certainly we need to figure out how to bring down the energy footprint of the depolymerization strategies a lot. And how to scale them up too. That's another big challenge, which I didn't talk much about. It's very important.
Yeah, thank you.
Mary, you had a question?
Yeah, first of all, excellent talk, Suzanne. Really, really good for everyone. And secondly, a quick question about your catalyst. In both cases, when you're getting out the long chain, materials at the end, you're using a platinum catalyst. Yeah. So obviously you wouldn't call it a catalyst if most of it weren't still there. The question is, how much do you lose of this material? Both in the process of making the first polymer, but also in the process of getting back out the products you're after.
Right. So that's a good question. Obviously, platinum is expensive and scarce. Our catalyst is completely insoluble in the liquid hydrocarbons that are made in the process. Okay. So we can very readily extract the liquid hydrocarbons and leave the catalyst behind. And the platinum in the hydrocarbon is undetectable. So as far as we know, we're not losing the catalyst. The question though is whether you can reuse it, right? It's not a catalyst unless you can, or it's not effective as a catalyst unless you can reuse it. And right now what we're having to do is clean it up, burn the hydrocarbons off. So, and then put it back in the reactor and then it works again.
Okay.
So the thing about platinum.
So you're losing some energy in that particular process. I mean, you're using energy.
Yeah, you have to regenerate the catalyst, and that is an energy consuming process, and you would like to minimize that. So you want your catalyst to be as long lived as possible. Okay. Now, people often ask me, can you replace the platinum with something that's more abundant, right? Yeah, that's a different sort of analysis, but it often ends up being, well, but platinum is so much better as a catalyst and it's so much longer lived that the energy footprint of using a tiny amount of platinum is actually less than using a lot more of another metal.
I actually wasn't going to go there.
Okay, then you've heard all of that story too.
I hear a lot about the cleanliness of the feedstock when you're talking about recycling plastics. And it seems to me that what you're talking about is really a reuse of plastic. It's kind of on the way to recycling. And so it's all in the same category from my perspective. And if for full recycling, if it has to be super clean on the feedstock, and I don't know if that's because the people that are collecting the plastic don't want rats to come and pick through the stuff, or if you actually have to have it clean when it enters into the recycling process. But could you talk a little bit about how prepared the materials have to be for the reuse cycle that you're proposing?
Sure. Actually, I'll talk about it both for this kind of chemical recycling as well as for the mechanical type of recycling. So I presented polymers as being just carbon-based molecules, but actually these polymeric materials have a lot of additives and fillers in them, which are there to adjust their properties. Sometimes they're aesthetic, sometimes they're functional, but they contain a lot of stuff. And that's intrinsic to the polymer. So no matter how much you clean your plastic, you're not getting that out. It's going to be carried along. When you mechanically recycle mixtures of polymers, you have unknown mixtures of additives in there. And that's one of the things that makes it hard to be reliable in the properties of the material that you're going to be making, the recycled material. In addition to that, you have all the other junk in there, you know, the traces of milk residue, the pizza toppings, you know, everything else that came along with your trash that have to be separated. And I would say we know how to do a lot of separations, but the more separation you do, the more expensive it is, right? And so the cleaner your material needs to be for your process, the more expensive that feedstock is going to be. The nice thing about the chemical recycling is that if you generate, so if I take polyethylene, which is a solid material, you can melt it, but it's still a very heavy liquid, and you turn it into something like propylene. Well, the propylene comes off as a pure stream, right? And we know how to make that stream even purer if we want to. We can do very good separation. So if you are making small molecules, you can actually purify those small molecules much more readily than you can purify these plastics. So we can actually make material which is indistinguishable from what we call virgin polymer from in this chemical recycling route. One problem, though, is that the additives in the polymer can stick to your catalyst, right? Catalyst is usually a very, very small part of this whole process, but it's critical because it's going to cause this reaction to occur. And if you have even traces of things in your plastic, which are catalyst poisons, sulfur is a fantastic catalyst poison, and sulfur is found in all kinds of biological materials, our food, for example. If that ends up on your catalyst, it'll kill your catalyst. So we need to either remove those things from the plastic waste, which is expensive, or we need to design catalysts which are very robust and they don't care and they're not deactivated. So where is the right, where's the right balance there? I don't think we've determined that yet. We're going to spend some money cleaning things up and some money, regenerating catalysts.
So if I remember your charts correctly, there was big activation energy to get it to the single stream or the single chain, and then you get a bunch of that energy plus some back for putting it into a poly chain, but what you just said is if you put it into a mono, you said if you reverse that cycle, it's super expensive energy wise. And I think your process avoided having to go back to the monostream.
It did because, well, we were using ethylene as a co-reactant. So that means there's energy involved in making that ethylene. We have to make that from somewhere too, right? You can make ethylene by dehydrating ethanol. Ethanol could come from fermentation, right? So there are other ways to make the ethylene, but it's a different process than just the depolymerization, which is the one you remember as being very energy intensive.
So then if you just go to what you want to do and you're proposing, which sounds amazing, how dirty can the feedstock be? In other words, with all the additives and not just the bio stuff, the milk residue, but the color of the bottle and all that stuff, right? That's the pigments.
So it depends very much on the process. I will say in my lab where we do pretty fundamental research, we either buy pristine plastic just to make the point that we can take it apart, or my students go around and choose, plastic bags and plastic wrap that they find around the lab, and they put that into the reactor. I think it's a different kettle of fish if you were to go to a municipal recycling facility and say, give me some of your garbage. That is different stuff. Okay. but it's something that we have to wrestle with. Can these kinds of processes do that? One that we're working on now is oxidative depolymerization. So we use air, the oxygen in air to depolymerize, and we can do that without a catalyst. And I'm very interested in that process. It's a radical-based process because we won't have these problems with junk. And there we have taken bottles that have labels with dyes in them and all kinds of things just quickly. And it works. So probably different processes will be suitable for different types of waste. I imagine there won't be one single solution for all of them.
So what's the time frame? It sounds like you're kind of at,
Sorry, I'm
little-
not sure if you can see my hand up there.
Robert, are you asking a question?
Yeah. So sorry, I'm not sure if I missed something, but it seems like you've just offered one possible path for recycling one particular kind of plastic. Is there a path for all these other kinds of plastic?
So there's a lot of people working in this field now. Okay, I was in it early, and so I got a few papers out before everybody jumped in, but there's a huge investment now and a huge energy around this. So as I said, the ones that I think are important to tackle are the plastics that are produced on a really large scale. They have a big energy footprint and they have a big waste footprint. So we're talking about polyethylene and polypropylene, which is the area where I work, but also polystyrene, polyvinyl chloride. Frankly, I would be happy if we just banned polyvinyl chloride because the chlorine in it just makes it everything nasty. But there are people trying to recycle polyvinyl chloride, and then PET. And the PET is actually not a polyolefin, it's a polyester. And the types of reactions that you want to do to depolymerize a polyester are different, but you can depolymerize it, get the monomers back, and use them to make new polymers. So each kind of chemistry kind of requires a slightly different approach, but the general theme in all of these is that you want to have a strategy which is fairly energy efficient and scalable to take these very large intractable molecules into small pieces that we actually know how to handle. And in terms of the time scale, when could this actually happen? I would say that the plastics industry would prefer that it happened yesterday, okay? But they don't know how to do it yet. So what they are doing, to my dismay, I think, is doing pyrolysis. They pyrolyze these materials, make them into liquids, and then they feed the liquids to what they call naphtha crackers. They do steam cracking to make monomers that they can make new polymers out of. It's a dirty process. It's a very energy intensive process. It's circular in a sense, right? The carbon ends up back in plastics eventually, but it's not good for the climate. So I think we can do better. But, you know, this is the problem with trying to change an industry this large is that you have billion-dollar plants that make this stuff. The capital investment is enormous, and to replace it is just astronomical. Dow Chemical is actually doing this in Canada. They built they announced they're going to build a net zero cracker for making net zero polyethylene. And the investment is $12 billion to build that plant. Okay. And they have 48 crackers. So 48 times 12, you can imagine this is not going to happen overnight. This is going to be a long, slow process. But it's one that's really important to start now because we need in 20 years to be quite a long way down this path, right? It's a big challenge.
What's the process for making it net zero? That means you have to have on-site renewable energy feeding that whole process, which means it needs to be electric, not fossil fuel.
Interestingly, they're not electrifying their cracker. There are other companies that are doing electrification. But they're actually, so when you crack ethane to ethylene, you make methane as a byproduct. They take the methane and they do autothermal reforming to make hydrogen and CO2. They burn the hydrogen to fire the cracker and they bury the CO2. That's their strategy. And just that modification is $12 billion.
That was the fossil fuel industry. The oil and gas, how are they seem like they would be at odds to the Dow Chemicals of the world, who are the processors. Because you're gonna lose that feedstock opportunity for the oil and gas industry.
Well, they're being charged now with pivoting to plastics as a replacement for their business making hydrocarbon fuels. Or they're thinking, we're going to continue to use those hydrocarbon fuels, but we're gonna bury the carbon. There's a carbon sequestration is one of the strategies that they're using.
I just mean it, oil and gas, the Exxons of the world versus the Dows of the world, are they aligned or are they at odds on moving to cleaner reuse, recycling?
Yeah. Are we gonna stop the recording here? Before I say something.
Well, thank you very much for your talk.